Once again, good morning, good afternoon, everyone. Welcome, everyone. Thank you for attending today's webinar. I'm Vamshi Domudalanen, System Applications Engineer at Vicor의. Today, I'll be presenting a topic, meeting DC to DC power system requirements in defense applications. And the agenda of today's presentation is, in the first few slides, I'll talk about the requirements in defense applications and filtering requirements to meet military standard emission specifications. And then in the following slides, I will introduce Vicor의 power components such as Milcott's input filter module, as well as DC to DC converter module. And in the next few slides, I will present typical emission test results that have been carried out on Milcott's input filter module in combination with DC to DC converter module. And then followed by a typical application and general layout guidelines for effective noise reduction. And finally, I will conclude my presentation with Vicor의 online tools. All right, let's get started with the requirements in defense applications. Defense applications such as radar, UAVs, and missile control are mission-critical applications which require highly reliable and highly efficient power supplies. Along with these requirements, defense applications are demanding SWaP-C requirements such as size, weight, and power. So the main goal of defense application SWaP-C requirements is to achieve or is to use a switching power supply with a reduced size, weight, and cost while maintaining higher output power capabilities. All these requirements can be achieved by using highly density power electronic switching power supplies. However, switching power supplies have a drawback of generating electromagnetic interference or noise that can interfere with the nearer devices. Therefore, switching power supplies in defense applications requires to meet certain military standard emission specifications such as EMC performance requirements and electrical power characteristic requirements. Along with these, switching power supplies also requires to meet environmental qualification requirements. Let's look more in detail about EMC performance characteristic requirements such as conductor emissions and conductor susceptibility. To understand this, we need to know what is the source of electromagnetic emissions or noise, and what are conductor emissions, and what are conductor emission regulations. Emissions or noise is internally generated in the switching power supplies as a nature of their operation of the circuit, as well as the result of parasitic capacitances formed in the circuit. The conductor emissions are the internally generated noise that propagate back onto the power supply through a conductive path. Thereby, the noise is transmitted to the devices that are connected to the same power supply and also can interfere with the close proximity devices. Thus, regulatory bodies such as U.S. Department of Defense put in place certain military standard limits for reliable operation of switching power supplies in harsh environments. Such MIL standard documents are MIL standard 461E or F, which describes the conductor emissions and conductor susceptibility limits. Similarly, the transient immunity or the electrical power characteristic requirements are documented in MIL standard 704F or MIL standard 1275D or E. The transient immunity is the ability of the system to withstand for any sudden change in the input voltage. And such transient immunity characteristics are documented in the MIL standard reference documents. Along with these, the environmental qualification requirements for switching power supplies are mechanical shock, vibration, temperature cycling, altitude, which are documented in MIL standard 810G. And most importantly, it is worth noting that not only the standalone DC to DC converter should meet MIL standard requirements, but also the overall system should meet MIL standard requirements. In this slide, I would like to discuss about the EMC standard requirements applicability in defense applications. Some of the defense applications require more conducted susceptibility or conducted emissions or radiated emissions or radiated susceptibility tests, whereas in general, the defense applications requires to meet the CE 101, CE 102, CS 101, CS 114, CS 115, CS 116, which are highlighted in the red text. From this slide, I would like to discuss more on very common conducted emission tests, such as CE 101, as per MIL standard 461 ERF. The figure on the left shows the conducted emissions plot for CE 101, and the emissions are plotted on a frequency versus limit level dB microamps scale, and the emissions are recorded on the input power leads as a measure of current through the power leads over a frequency range of 30 Hz to 10 kilohertz. And the curve 1 is the limit line for the systems with input voltages greater than 28 volts, whereas the curve 2 is a limit line for systems with the input voltage less than or equals to 28 volts. The figure on the right side is CE 102 conducted emissions as per MIL standard 461 ERF, and the emissions are plotted over a frequency range of 10 kilohertz to 10 megahertz, and the emissions are plotted over frequency versus limit level dB microvolts scale, and the emissions are recorded on both input power leads as a measure of voltage across 50 ohm terminations of line impedance stabilization network. And the limit line, the basic curve shown, is a limit line for the systems with input voltages of 28 volts, whereas certain relaxations, limit relaxations, are applicable for input voltages greater than 28 volts. For example, for a 270 volts DC system, a 10 dB limit relaxation is applicable, and the limit line for 270 volts DC system is shown in red. Similarly, the conducted susceptibility CS 101 is also from a MIL standard 461 E and F, and the emissions here, the susceptibility test results are plotted over a frequency range of 30 Hz to 1 kilohertz with the frequency versus limit level dB microvolts scale, and the curve 1 shows the limit line for systems with input voltages greater than 28 volts, whereas the curve 2 is the limit line for the systems with the input voltages less than or equals to 28 volts. And the emissions are plotted. The emissions are conducted on positive input lead only, whereas the emissions are recorded with a defined noise signal injecting into the equipment under test through positive lead, and the the emissions are recorded at the output of the equipment under test. Similarly, the electrical power characteristics such as transient immunity are from MIL standard 704F for high input voltage DC systems. The figure on the left shows envelope of normal voltage transients for a 270 volts DC system with a time duration of 20 milliseconds with an amplitude change from 280 volts to 330 volts DC, whereas the under voltage transient duration is 30 milliseconds with an amplitude change of 200 volts to 250 volts. Whereas certain abnormal transients are also applicable for transient immunity tests, which are stated in MIL standard 704F standard document in the table HDC 1053 and HDC 3023. Similarly, for the low voltage 28 volts DC system, the transient immunity levels are from MIL standard 1275 MIL document. The figure on the left shows envelope of surges for 28 volts DC system, whereas the over voltage transient is for a 50 millisecond duration with an amplitude of 100 volts, and with the under voltage transient with an amplitude change from 18 volts to 20 volts in 100 millisecond duration. The figure on the right shows the envelope of spikes in normal operating mode for a 28 volts DC system with a time duration of 70 microseconds and with an amplitude of 250 volts DC. And, to meet the MIL standard requirements specified in the previous slides, an EMI input filter is required in front of a DC to DC converter, whereas EMI input filter typically consists of several discrete filtering components and transient protection circuitry, which is shown in the dotted line. As mentioned in the earlier slides, the DC to DC converters is a source of the noise or the electromagnetic interference. The DC to DC converters basically generates a differential mode and common mode noise currents. These noise currents are typically at harmonics of the switching frequencies. Therefore, to attenuate the noise generated by the DC to DC converter, the differential mode elements or common mode elements are necessary. The differential mode noise is a result of operation of the circuit, which is present between the positive lead and the negative lead of the DC to DC converter, and can be attenuated by using differential mode filtering elements such as the leakage inductance offered by the common mode choke and the X capacitors, which are shown in blue color. Typically, the leakage inductance provides a high impedance path to the differential mode noise, whereas the X capacitor provides a low impedance path to the differential mode noise, and the differential mode noise is shunt to power ground by the low impedance X capacitors. Similarly, the common mode noise is a result of the circuit parasitic capacitances and can be attenuated by using common mode elements such as common mode choke and Y capacitors. Here, the common mode choke provides the high impedance path to the common mode noise, which is propagating back to the power supply through both positive and negative leads. whereas the Y capacitors, which are placed close to the DC to DC converter, provides low impedance path to EMI ground or protective earth, which shunts the common mode noise currents. And the transient protection circuitry, which is shown in the block, is an active circuit that suppresses the transient energy to acceptable limits of the DC to DC converter. And the common mode as well as the differential mode noise currents that are flowing back onto the DC power supply is a measure of conductor emissions, whereas the common mode as well as differential mode noise flowing from power supply towards the DC to DC converter is a measure of conductor susceptibility. The noise generated by the DC power supply is attenuated by using the common mode choke as well as X and Y capacitors, which are placed closer to the DC power supply. And the EMI filter and the DC to DC converter can be replaced with the Vicore integrated power component solutions, such as EMI filter can be replaced with Milcott's input filter module, whereas the DC to DC converter can be replaced with the DCM in a VIA package. And in the following few slides, I'll discuss more about the Milcott's input filter module and its features, as well as the DCM in a VIA package and its features. Milcott's input filter module is further referred as MFM, is an integrated solution, filtering solution, which is specifically designed to meet specific MIL standard requirements when used with the DCM in a VIA package. The Milcott's input filter module is available in two different input voltage ranges. The low voltage MFM is available in 16 to 50 volts DC input range with a nominal input of 28 volts. And the HV MFM or high voltage MFM is available in 160 to 420 volts DC range with a nominal line of 270 volts DC. And the 16 to 50 as well as 160 to 420 volts DC are typical defense application requirements. So the comparison table here shows the HV MFM as well as the LV MFM in detail, whereas the maximum power capability of the HV MFM is 640 watts with a maximum output current of 4 amps with an efficiency of 99.4%. And similarly, the LV MFM has a maximum output power capability of 350 watt with a maximum output current of 22 amps, and the efficiency is up to 99.6%. And the operating temperature range of the HV MFM and LV MFM complies with the military grade temperatures, which is minus 55 degrees C to 125 degrees C. Whereas the safety dielectric withstand voltage from input to output leads to EMI ground is 2121 volts DC for HV MFM and 1500 volts DC for LV MFM. And the MFMs are available in different mounting options such as a PCB mount and chassis mount version. And in the following slides, I would like to provide some information about product features, advantages, and electrical characteristics of Vicore DC to DC converter modules, which are further referred as Dcms. Dcms are standard DC to DC converters, which provide isolation from high side to the low side, and also provides a regulated DC output voltage with a wide input voltage range in unregulated source. And DCMs are available with multiple output voltage ranges. And DCMs uses high switching frequency zero voltage switching topology. Due to its high switching as well as zero voltage switching topology, the losses in the converter are low. Therefore, the efficiencies are up to 93%, and also it can DCMs are high power density devices, which are available in 3 different temperature grades, such as industrial grade, commercial grade, and military grade temperatures. And which are the DCMs are available in different packages, and the VIA DCMs or DCMs in a VIA package is available in multiple mounting styles, such as PCB mount and chassis mount. The figures of the PCB mount version as well as chassis mount version can be seen on the right corner. And Vicor integrated package, DCM in a VIA package, provides a better thermal solution, as well as it provides 4 sides shielding of the to the DC to DC converter, which can potentially reduce the radiated emissions that are caused due to the high switching frequency action in the DC to DC converter module. Here are some of the electrical characteristics. The low voltage products, the low input voltage products, which are from 9 to 75 volts range, are available in a 3623 chip package as well as 3414 VIA package, and the output voltages available are from 3 volts to 52.8 volts range, with a maximum power of 320 watt. Similarly, the high input voltage products are available from 120 volts to 420 volts input range, with a maximum power capability of 600 watt. With the chip package comes in a 4623, as well as the VIA package comes in a 3714. And some of the typical applications of a DC to DC converter module are in industrial or telecom. DCMs can be used as a constant current device or constant voltage source for battery charging applications. DCMs are a good fit in defense applications due to its reduced size, weight, and higher output power capability. Such defense applications are ground-based vehicular systems, such as communication systems or targeting systems, and flat panel displays, RF jamming, and GPS mobile tracking. And DCMs are also a good fit in airborne applications, which requires less payload or less weight, such as tethered drones, as well as legacy airborne systems. Some of the advantages of using DCMs are high power density, cost-effective solution, and easy to design a power system solution, fast design time, and low design risk. The comparison table in this slide shows the standards that are met with LV-MFM plus the low input voltage 28 volts DCM in a VIA package with M grade as well as a T grade version. Similarly, what all standards are met with the HV-MFM plus DCM in a VIA package, which is 270 volts with the nominal input. The HV-MFM plus M-grade DCM in a via package can comply with the conducted emissions, conducted susceptibility as per MIL standard 461 ERF, whereas, and also it can comply with the transient immunity MIL standard 704F. And the operating temperature range of M-grade via DCM can go up to minus 55 degrees C, which is a typical requirement in defense applications. Whereas HV-MFM with the T-grade does not comply with the operating temperature range, whereas it complies with the EMC performance characteristics. Similarly, the LV-MFM plus M-grade DCM in a via package will comply with the EMC performance requirements, and but the LV-MFM with T-grade DCM in a via package does not comply with the operating temperature range and the transient immunity as per MIL standard 1275D or E. From the following slides, I would like to discuss more about the test setup for conducted emissions, which have been carried out on the high voltage MFM plus DCM in a via package. And a typical test setup consists of a DC power supply, which is placed outside the Faraday cage. The Faraday cage is shown on top left. To avoid any switching frequencies or any noise coming from the DC power supply, therefore the DC power supply is placed outside the Faraday cage, and the Faraday cage or the screen room is equipped with line filters, DC line filters, which attenuates high frequency, low frequency, as well as the radio frequency noise coming from the DC power supply or coming through the environment. And an individual line impedance stabilization network is placed on each line, the positive lead as well as the negative lead, to provide a definite impedance looking back into the power supply. The typical requirements for military standard listen impedance is 50 ohms, as well as the output of the listens are then connected to the equipment under test, which here in this case is the HV-MFM and the DCM in a via package. A typical CE101 test setup consists of a 50 ohm termination on one of the line impedance stabilization network, on both line impedance stabilization network, and the emissions are recorded as a measure of current flowing through the positive lead as well as the negative lead by using a EMI receiver. And the typical CE102 test setup consists of a 50 ohm termination, and whereas the emissions are recorded using an EMI receiver as a function of voltage across a 50 ohm termination of the positive lead or negative lead. Here are some of the test results for high voltage MFM plus a 300 volts V in DC system with a output voltage of 28 volts. The figure on the left shows the typical emission test plots for a positive lead with a 0% load, and the emissions are plotted over a frequency range of 30 Hz to 10 kilohertz as a function of frequency and dB microamps, whereas the red line shows the MIL standard 461 ERF limit line, and the blue emission plot are the recorded emissions for HV-MFM plus DCM in a via package. Similarly, the tests have been carried out on the negative lead with a 0% load, and from both positive lead as well as the negative lead emission plots, it can be observed that the emission levels are more than 20 dB below the limit line. Therefore, the system complies with the CE 101 as per MIL standard 461E or F. Similarly, the tests have been carried out for 100% load on positive lead as well as negative lead, and the emission plots confirm that the system complies with the MIL standard 461E or F CE 101. Similar test results have been recorded for conductor emissions CE 102 on both positive lead as well as negative lead at 0% load, and the emissions are plotted over a frequency range of 10 kilohertz to 10 megahertz with the frequency versus dB microvolt scale, and the emissions in the low frequency shows near to the limit line, whereas the overall test setup has a base emissions, and on top of that the emissions of the EUT are plotted. Therefore, the emissions are very close to the limit line, but still less than below 10 dB margin. Similarly, for the negative lead, the emissions are below 10 dB margin. The results on this figure on this slide shows typical test results with the 100% load for a CE 102 as per MIL standard 461 ERF. And it can be observed that there is a sudden change in the tip emissions from at around 40 kilohertz. This is due to the change in the bandwidth shift of the EMI receiver. And the plots shows that the emission results comply with the MIL standard CE 102 limits. And here are some of the transient immunity test results for a 28 volts V-in DC system. The typical test setup was LV MFM plus 28 volts DCM in a via package with 12 volts output. The figure on the left shows a high over voltage transient with an amplitude change from 28 volts as shown in the dark blue, from 28 volts to 100 volts with a duration of 50 milliseconds, and the light blue curve shows the transient suppression from 100 volts to 75 volts, which is acceptable range of the downstream DC to DC converter. And the green curve shows the 12 volts output, during the transient conditions. Similarly, the plot on the right shows the low voltage transient, which is 60 volts DC with the time duration of 350 milliseconds. The amplitude change is from 28 volts to 60 volts, and the light blue curve shows the transient suppression of 60 volts to 58 volts, which is again an acceptable range of downstream DC to DC converter. In this slide, I would like to present a typical application such as radar in defense applications, which requires pulse load characteristics and also requires to meet certain MIL standard specifications. as previously discussed. And here is a typical block diagram which shows a DC power supply with high voltage MFM and the DCM in a via package supplying the pulse load characteristics, which is shown in the bottom of the slide. And the general layout guidelines are also an important factor that needs to be considered while designing the overall system. The layout, the PCB layout, has an effect of reducing or increasing the radiated emissions. The poor layout can cause increase in parasitic capacitances or coupling capacitors formed in the in between the PCB traces, and can potentially trigger the radiated emissions. Therefore, here are some of the considerations that needs to be keep in mind while designing the PCB boards. One of them is adding ground planes. Adding ground planes on outer layers will potentially suppress the high frequency noise coming out of the signal traces, which are buried in the inner layers. And adding a ground fill. If there are no traces in some areas of the PCB, adding a ground fill will reduce the emissions. And susceptibility. And if ground fill is not properly connected to the ground plane, can increase the emissions and susceptibility, and can also increase the crosstalk between the power layers or the signal layers. And also, it is worth noting that connecting the ground planes by using multiple vias, which will reduce the inductance of the trace. And also, the other point is to eliminate return path discontinuities. And for higher current carrying capability, the number of layers can be increased so that the number of copper traces to the input to the power plane or to the ground planes can be increased. And finally, I would like to conclude my presentation with providing some information on available Vicor online tools. The Vicor Power Bench consists of a power system designer, which can be used to design a power system using building blocks which are available online. And the whiteboard provides information, or whiteboard provides provides flexibility to the designer to use multiple outputs or multiple inputs in a simulation environment. For example, an MFM with a DCM in a via package is shown, where the source and the load are connected, and you can analyze the electrical performance characteristics using whiteboard. Similarly, the startup as well as steady state conditions and also the thermal operating ranges can be simulated in simulators, and various app notes are available on how to use Vicor power components as well as general theoretical concepts which are applicable for designing a good power system. And here are some of the useful links which directly links to the family pages of DC to DC converter modules, as well as Vicor's input filter module, and the app note MIL, EMI, and transient solution describes about the requirements for requirements that needs to meet in certain applications, in MIL grade applications. And that's all for now. And thank you for joining today's webinar.